classification.
Yes.
And today regression problem, two problems they used, neural networks and perhaps comparison also with SVM.
Okay.
So you may start, Professor.
Yes. Thank you. Okay, so participants, do you have any questions regarding the last class? Anyone having any doubts? Was it okay? Adam techniques, yeah, we'll discuss today. Okay, this Adam techniques, all this optimization we'll discuss today, Dipti. Yeah, whatever we have covered yesterday regarding that, okay, those concepts. Anyone having any doubts? Okay, Vidya Vanu, we say that all clear. Fine, very good, excellent. Great. So everything clear, right? That's good. Usually with one lecture, people cannot clear everything, but you are all good.
No, you have been clearing the doubts during your session, so that makes it very interactive, and I am sure that participants have understood the concepts.
Yes. No, they are sending messages also, madam. So they say that, yeah, no doubts, nothing.
Yeah, that's what I was saying.
Okay, thank you, madam. Yeah, we can start. Thank you. So we have covered the basics of neural network yesterday. Plus, we started with perceptron, then training of perceptrons. Then we talked about multi-layer perceptrons, parameters. Then what is hidden layer? How can we make this MLP multi-layer perceptron trained on some data? Those are discussed. Okay, right? So today we are going to discuss some more stuffs of neural network. So in this agenda of today, we have this following. First, we are going to discuss about loss functions. Obviously, what are the different loss functions we can consider for this neural network? Then what are this overfitting and underfitting? Then regularizations. Regularizations you have, for example, how can we get better accuracy? Okay, these regularizations, optimizations, all actually help you to get you results faster and better. And then for that, we will also discuss about data augmentations and dropout optimizations. Okay, so these are the topics we are going to cover today. Okay. So we had learned about this multi-layer perceptrons yesterday, and in this multi-layer perceptrons, if you see that input was X, and these are the features X1, X2, all this. Okay, so you can consider it's an X. And if it is a multi-layer perceptrons with some layers, hidden layers, and then you have the output. Okay, so output will give you the results. Now, there we considered one thing that we have discussed about the error functions, right? Error functions means we said that okay, what is the error? Means what is the predictions and what is the actual output. Because we talked about, for example, error as y minus t whole square, okay, and then half, okay. So it's an error. So that was the error, okay. So that you can consider this is a loss function, okay. This is the loss, okay. So whatever you make an architecture, you build one architecture based on this architectures, okay. So you had some actual outcome, okay. Y is the actual outcome, and you are predicting something, okay. So f theta x is the predictions, it is the predictions, okay. Output is the predictions, and what is the error, okay, that we call it's a distance or error functions. This could be this could be talked about L theta, where theta is the parameters, means number of parameters. Parameters are actually W's, all those W's, okay. These are the parameters. We can write W's or we can write theta. So now in this, I'm just changing it to theta. So error function is the distance function, same. So it is prediction and actual functions, actual results. What is the distance, okay. So if you, how do you calculate the distance? So y is the ground truth and f theta x is the predictions. Now there are different kinds of error functions. Sometimes we talk about L1 distance or absolute error. Sometimes we talk about squared error. Sometimes we talk about cross entropy error. Okay, so absolute error or squared error, these are used in regression, and cross entropy error, this is used in categorical output or when you go for classifications. Classification means when I'm saying the prediction is, for example, in last day we discussed about Salman, but I'm predicting as Rahu. Okay, this is the classification error. There we use this cross entropy error. When we have this regression means, for example, you have seen this about flat price, okay, or weather forecast. So you are predicting something, okay. So you have this actual outcome and you are predicting something like this. So what is the error? Okay, so you will consider this error as absolute error or square error. So what is the distance? This distance you can consider it's a simple distance, then it's a absolute error, means plus, whatever, if it is minus also, then you can consider it's a plus, then it's a absolute error, and then you can consider it's a squared error, means whatever distance error is there, you just make it square. So that will be L2 error. So there are different kinds of error functions are there. So if I'm just talking about this absolute distance or absolute error, so you have, for example, this is the yi minus theta, f theta x, okay. So this is the, if this difference, if I'm just considering the difference, if it is positive, it could be positive or negative, okay, whatever. If this y is, for example, y, consider this flat price or weather forecast, okay, the temperature. If it is large or it is smaller, okay, so you'll get the difference positive. So here, if it will be, the difference is positive. If it is higher, it is smaller, then you'll get negative. Whatever it is, the loss will be always okay, positive. Okay, so this is the loss function. So it is absolute error. Okay, so I'm just considering the error function as yi minus f theta x, means this prediction x. Instead of f, you can consider this is the prediction. Okay, so prediction, and yi is the actual. So this difference, if you consider it's an absolute value, then it will be the absolute error. you can consider this error function as square term. Okay, so in this regression, if you have the difference, okay, so if it is difference is something like 1 or 2, this difference, and then you consider square term, so this loss will be large. So if the difference is smaller, the loss is actually going to be large. Okay, so if you in the positive negative both sides, the square is actually your loss is larger. So that means you are making more penalty to the loss functions. Okay, so based on the error. So if you have the error prediction is, for example, 1 or 0.9, and you are predicting 0.4. Okay, so the difference is 0.5, and then it will be something like this. And whenever the prediction is a little larger, then the loss is going to be large. Okay, so if it is 2, then the predictions loss functions will be large. So these errors are all calculated using this formula, and you know that how you can modify those weights. Okay, so WYK, WJI, if you remember, those parameters I need to modify. So those parameters will be modified based on this loss functions. So these loss functions either can be absolute or it could be squared. There is another, so here it's mentioned as bigger difference between predicted and ground truth leads higher loss. Okay, so when the difference is higher, so if I'm just considering L1 loss or simple loss, then it will be loss will be like this, simple. Okay, but when I'm considering this squared loss, then the loss will be large. So for the same difference for absolute distance, the loss will be, for example, if it is 1.5, it will be 1.5, but for squared loss, it will be 2.5. So I'm giving more penalty. So this gradient, okay, this gradient or this weight functions will be adjusted better when I'm considering this square distance, right? There is another one, that is cross entropy error. You have any doubts? There is another loss function. This is cross entropy or log loss. This is used mostly for categorical data. For example, if I want to classify some objects, okay, like fishes, okay, so it's a roe, sea bass, salmon, these kinds of fishes. Or if it is a fruits, then it's a mango, okay, one of the category. Okay, so for example, if you are having some actions, so whether I'm running or I am doing jogging or walking, so one of this category, it will not be a it's not a probability. Okay, it's not a simple decimal numbers. Okay, or some floating numbers. Okay, so I will get one absolute class category, whether it's a dog, it's a cat, it's a horse, whatever it is. So there you have this binary, or it could be multi cross entropy. So what it does, this loss function is used using the formula 1 by n into yi log pi plus 1 minus yi log 1 minus pi. Okay, so if it is for two categories means either one category will be 1, another category will be 0. Okay, so if it's I'm considering this one is salmon, then 0 will be log. Okay, one of this category. So, and when I'm considering for loss functions, okay, the error function is calculated using this formula. So you see here, there are two terms, yi dot log pi plus 1 minus I dot into log 1 minus pi. It is into, okay, multiplication. Yi means actual class and pi means predictions. Okay, So when I'm using this multi-MLP, okay, multi-layer perceptrons, then the results may be in the probability like 0.7, 0.8. Okay. So what will happen? So it will also say we have the class level. So for example, if I'm saying that it is a dog, okay, so or it is a salmon, okay, salmon, I'm saying that it is a 1, and then the actual value is actual class level is salmon, and I'm predicting the salmon as 0.2. Okay, so actual class is salmon, so it is y. So 1 minus yi, it will be 1 minus yi, it will be 1 minus 1, it will be 0. So 0 into this, it is cancelled. So one of this term is only used. If I have the actual class as 0 or low, then it will be 0 into log pi plus 1 minus 0 into log 1 minus pi. So this will be cancelling, and then it will be 1 minus 0 means it will be only log into 1 minus pi. So either log pi will be used or log 1 minus pi will be used. Okay. So whatever you do means whatever class levels you have actually, so you will get only one of these predictions. Either it will be 1 or it will be 1. 1 means either you will consider this log pi or you will consider log 1 minus pi. Now pi is the predicted probability of class 1. Okay. So, and then if you have this probability of class 1, then you can consider the probability of class 0 as 1 minus pi. Now, what does it mean by log pi? Okay, so what is log pi? How actually it will give you the error? Okay, so as we have discussed, this error, if you have this difference based on this loss is actually larger. So now you will see that whatever predictions it gives, okay, so the predictions it provides, then how actually you will give the loss. So here the loss is using the log formula, log. Okay, so log of the pi. Now, if you predict the probability, the class level with probability of 0 or 0.1 something, that means it's a very low. Okay, so if you have the class level 1 and then you are predicting the class level 1 with a probability very small, then then your loss will be very large. You see, this is the loss log functions. Okay, so if you calculate the log functions, if you see the log functions, okay, so it's log 0, you know that log 0 is infinity, and log 1 is 0. Okay, so it is log 1. So log pi, if you predict pi with 1, that means it is 0. If you predict it is with 0, then the log 0 will be infinity. So this is the log functions. Okay, so these log functions we are using. So when you predict, okay, yes. Hello.
Just a minute.
Hello, any doubts? Do you have any doubts?
So in case you have any doubts, please drop it on chat. Yeah, there is one question. Sir, what about loss in multi-class classification?
Yeah, that we are going to discuss. First, let's discuss about this binary. Okay, first, then we will discuss. Is it okay? Did you understand this? So when we have when we are going to use this log functions, so when the prediction probability is close to 0, Okay, 0 means infinity, and then when it's close to 0, you see this loss function, it is very large. When the prediction is close to 1, it is 1, then loss function is 0. Okay, when the prediction is close to 1, then loss will be close to 0. Okay, so this is the cross entropy error. Okay, similarly, if we use the 1 minus log 1 minus y into log 1 minus pi, so it will happen in the same way. So your curve will look like, sorry, your curve will look like this. Okay, so when you will be log 1 minus pi, okay, so log 1 minus pi. So if you have the probability with 0, then you will get the loss as close to 0. And when the probability is high, 1 pi is very high, that means 1 minus pi will be close to 0. Then it will be, loss will be large. Okay, so it's just opposite. So this model, this cross entropy model, is used for categorical data. We have discussed about 2 categories. Either it is, for example, horse or it's not horse, it's a dog or not dog, it's a cat or not cat, it's a 0 or not 0. Okay, or for example, you can say that it's a rohu or salmon. Okay, or you can say that mango or lychee. Okay, so these 2 categories when you have, then you can use these kinds of loss functions. It's a binary. Then how can you use the multiple cross entropy, multi cross entropy error? Okay, so when you have more than 1 categories. So what's your answer? Some of you can answer this? Yes. Anyone? 1 class compared with many. Multiple binary. Yes. So you can do, yes. So some of you, yes, both are correct. Okay. So either you can do it in a 2 way. Either you can go for 1 versus all, or you can go for 1 versus 1. Okay. There is another approach. Okay. So it's basically, you can use in the loss functions. Okay. So in this, you have 2 categories. Okay. So multiple categories. When you have this, one is you can, what we are discussing, y is the actual, and you have this predictions, the pi. Okay, or no, we can say that its prediction is something like y I hat. Then we can use, it's a summations of all these categories. Okay, so it is y into log of y. So either one of them will be 1, or our remaining will be 0. So whichever category, so one of them will be 1 and remaining will be 0. So whichever we will be considering, that part will be only providing you the value. Okay, these predictions, loss. Others will not provide any contributions. Okay, this will not give you value. So it is similar to your binary cross entropy error, but it is extended to multi-class. Okay, so as we are discussing about 2 levels, y into log pi, so we'll be using, it is like multiple. Okay, y into log of predictions, y hat, or you can consider y of log of pi. Okay, so one of them will be 1 and remaining will be 0. And based on this, you will consider the loss functions. Samir, is it okay? Do you follow? Okay, great. So as we have discussed here, one of this category will be 1. So in multiple category also, one of them will be 1 and remaining will be 0. Now let us discuss about this overfitting, underfitting. Okay. So when we have the training data, so as you know that when we will be working with this with a data set, I think you have got the idea of data sets. So data sets you have, for example, if I'm just talking about this MNIST OCR data set, okay, character recognition data sets, where you have some training data and a part is testing data. Okay, and then you create your model using this training data. Okay, so you devise your architecture, develop your architecture based on the training data, and then you test your accuracy on this testing data. So sometimes you will have also a validation data set. Validation data set, the purpose of this validation data set is when you train on this training data set, okay, so how will you know that which model, which architecture is the best? So you will be using the validation data set for testing purpose. You will be checking that. So for example, in training data, you create a model. Okay, so you create a model M1 and you test with these validation data sets and see what is the result, accuracy 1. From this training one, you create another model M2 and you test with this validation data set and you get another accuracy A2. So you can create a set of models and see which model is the best. And that model, so for example, your M4 model is the best. And that model you will be using for testing data set. And that is the final. Okay, so this model is the final. And that model you'll be using for testing data set to get the accuracy, right? This is the way we do performance measure of any data set. Now, when we have a data set and we create our models, different models we create, some models may be very simple. Okay, some models may be very simple, like if I create a models with a two perceptrons, okay, one layer models. Okay, so my model is something like this. You have some input data, and then I create a perceptron. Okay, this is the results. Okay, so I have this 3 input exercise, and this is the my model. Okay, simple model. So this model will give me a very simple results. Okay, a simple line. Okay, this is also a correct. Okay, so single simple model will give you some results, but this will not be good results. Okay, so what will happen? So if you have the data something like this, you will get the line. Okay, so like that, and which will not be able to separate the data properly. So this is called underfitting, means that separator, the predictions is not good. So this is not good in the training data set, and it is not good for the testing data set as well. Okay, so this kinds of model is not good for training as well as in testing. When you have a model which is very much overfitted. Overfitted means when I have three input data, and I am creating, for example, so many neurons, okay, in first layers, and then another layer with another set of neurons, okay. So I can develop so many, okay. So and then another third layer, fourth layers, okay. So here the number of weights are large. So your results will be very good in that data set. So in that training data set, okay, so whenever you increase the neurons, okay, or this layers, then your accuracy will be very good, because your line separator from this positive data and negative data will be very much fine tuned. Okay, so this is very much fine tuned with these kinds of data. Now this is the separator. Now if you have a new data comes, so this is the in the validation data, you get these kinds of model. Now in your testing data, if it comes, and testing data, for example, a data comes like this cross here, because the separator is such tune that it provides the line in this way. So even if the line, if the cross is in this part, in this region, still it will be able to, it will not be able to recognize properly. It will classify it as circle. So this is not good for the testing data set. It is good in the training data set. Okay, so this is called overfitting. When we have lots of parameters, okay, when the number of parameters, number of weights is large, then it goes for overfitting. When the number of parameter is small, then it goes for underfitting. Means the model is not able to predict in the training data set as well as in the testing data set, because it is very simple. The model is very simple, so it will not be able to classify even in the training or in the testing data. So we need some model which balance, okay. So we will require a optimized number of neurons, okay, and different layers, such that it is doing some error, okay, in the training. It will not predict everything correctly, okay. It is not very good in the training, but in the testing also it will not be very poor. In the testing also it will be good. So we want some models like this, okay. So we do not want a very high accurate or overfitted models. We need some good model which will be showing results in the testing data good, okay. So this is we want. So that's why even if you can increase the models, and we see that, okay, so if we increase the neurons and then increase the parameters, we can assume that our model will be very good and it will give you very good results. But in reality, it will give results in the training data set, but it will not give you the data in the testing data set. Is it okay? Did you follow? Which model function is best among the three? So of course, this good fit, we want the good fit, okay. We want a model which is not underfit, not overfit. We do not want this underfit or not overfit. We need some model which will give us results on the testing data set. Okay, I want, because in any data set, the model's accuracy is measured based on the testing data set's results. Okay, whatever you do in the training data set or validation data set, it doesn't matter. You can get 100% accuracy on the training data set, but your results should be good in the testing data set. Our main challenge is in the testing data set. If your model gives 100% result in training data set, but in testing result testing data, it gives you 40% accuracy, it is not good. But if your model is 80% good in training data set and 70% good in testing data set, this is better. So we need some models which is working in testing data set. Okay, so for that we need a not a underfitting, not a overfitting. We need one good fitting. Okay, one over optimized one. So where the number of parameters will not be. We'll discuss this. Okay, Shyam Deshmukh. So we'll discuss this application later. First, let us understand the theories. Okay. So underfitting happens when a model cannot capture a proper relationship between input and output. The model performs badly on both training and testing data. It occurs when a model is too simple. Okay, so when it is too simple and it cannot capture the characteristics of the training data. So this is the problem of the underfitting, because the number of parameter is very small. Okay, so the number of parameter is very simple, small, and then it cannot understand. Okay, so how actually it will find the separator. So if you have something like some points like this, okay, so but your model is giving you the predictions something like, okay, so something like this. Okay, so it is not correct. It is very simple model. We do not want a simple model. Okay, we want a better model. Okay, so because we can increase the neurons, but if we can increase, how much we can increase? We cannot increase by, if we have a resource, we cannot increase like so much. Okay, so it should not be overfitting. It happens when the model learns noise or random fluctuations in the training data as concepts. Noise or random fluctuation means, as I was telling, that for example in this data, this could be considered as noise. Some of this data could be considered as noise. If it is noise means some data are crossed, but you captured them as circle. So because of the circle, because of overfitting, this will learn the curve like that. Okay, they separated in this way. So this is not correct. Okay, so it will learn also noise. And then in the testing data, if the data comes in this way, okay, so this will be captured as or recognized as circle, but this is not correct. Now let us see in the regression problem. Regression problem also you have the similar things. Okay, so when you have this overfitting, underfitting, so let us consider that you have the data, and then you have seen about this. So you have some data, and then you want to do a fitting. Okay, so if I do a fitting, okay, so if you have the model is very simple, if your model is very simple, then it will make you high bias. High bias means it will cannot capture well on new data. Okay, so the model is very simple. Okay, the model is very simple. It will not capture the new data. Okay, so this is the high bias because very simple. And when it is the overfitting, you have so much parameters, so it will be tuned to all the noise and data. So it is perfect for that data set. But if you give a new data set, then it will not work. Okay, so here in this overfitting, okay, so it will consider a high variance. High variance means shows a large variation in the prediction of the target with change in the training data set. So when we change the data set, training data set with some another data set, you will see that the variance, this error will be large, because it will not, because with the small data, it will not be able to capture. That we have understood. Okay, so this is the variance and bias. So for good fitting, we need low bias and low variance. Low bias means when you will give a new data, so the predictions, okay, so predictions will be not very high compared to the actual, and the variance will also be low. That means if you change the data from training to validation, then also the error will be lower. So you have this, while making predictions, a difference occurs between prediction value made by the model and actual values. And this difference is known as bias error. Okay, so what is the actual and this is the predictions. Okay, this is the prediction and this is the actual. So this is the bias error. A high bias model cannot perform well on the new data. Okay, so as we have seen, if it is a very simple data, it will not able to capture. And variance also, if it's very much means very high, it is very much tuned, overfitted, then this will give you the results on that data set. But if you have a new data set, this will not perform well. So there also it will give you high variance. If there is a 20 difference in accuracy, is it good fit? 20 difference. I didn't understand, Lina. What do you say? What do you mean? If there is 20 difference in accuracy. 20 difference means? Can you unmute and talk? Or you write properly? Training accuracy and testing accuracy difference. Yes, training accuracy and testing accuracy difference. Yes, sometimes, yeah, I understood. So training difference and testing difference, that we are going to discuss. Sometimes you will see that when we train, okay, so when we train on the training data set, okay, so then the models is something like this. Okay, so if you have the number of parameters, it is the number of parameters, means number of weights. When your number of parameter is low, small, okay, 1 or 2, then it is an error. Okay, so you will have the error. When the number of parameter is small, then you will have a lot of error. Then the number of parameter is low, then you will get small error. The error will be reduced. And then when you are going to increase the parameters, then in the training data set, it will be very small. Okay, but it will happen in the testing data set. In testing data set also, when the number of parameter is small, then you will also get larger. Okay, but when you will increase the parameters, then you will also get less error. But after sometimes when it starts overfitting, you will see that error is going to increase. Okay, so that is possible in the testing data set. So you have to check at what point this in which number of parameters your testing data result is not going to increase. Okay, so it is possible that when you increase your parameters in the training data set, it is a training data set. In the training data set, the accuracy will always be smaller, okay, because it is getting overfitted. It will be overfitted, so it will be small and small. But in the testing data set, it will be it will not work, because with that parameters there will be a lot of overfitting, and it will be tuned, and it will not recognize those data in the testing data set properly. So the error will be shooting up. So there you have so there you have these regularizations. Okay, so now you have this regularization, that how we can control that how many parameters we need. Okay, so what is the parameter? How many parameters we need, so that we will not have underfitting and will not have also overfitting. So there we have that I was discussing. This is the error. Okay, so training data, and this is the your error. Okay, generalization error or this testing error. So at some point you will have this underfitting, and then you will start having overfitting. So you have to stop somewhere. So there are different, how will you stop? Okay, so where to stop? So there are different criteria, techniques for this regularizations. Okay, how will you know that where to stop? There are 4 different approaches: early stopping, data augmentation, and dropout. Okay, these are the 4 approaches, and many other approaches are also there. Some of these approaches you can consider. These are the techniques for regularization, means you can get the results. Even if it is overfitting, it will not it will work. Okay, so it will not go for more error in the testing data set. That's actually regularization. How will you control those parameters? So early stopping is very simple. As I was saying, that we have already discussed, right? This one. So when we are going to train, okay, this neural network that I have been talking, this is the training error and this is the testing error. So we know that when in the testing data set, it starts shooting up. Okay, so that is a point when the network stops generalizing and starts learning statistical noise. Statistical noise means it's actually overfitting. So the early stopping means we can stop there. So our number of parameters will be stopped, or this epochs or this learning rates, this will be stopped at that point, and based that models, whatever training data we have, those will be used for the testing. This is the early stopping. And then data augmentation. Data augmentation means when we have some data and we use the parameters. Okay. We are going to discuss later. So data augmentation means so when we have a data set, okay, so we have a data set, we have this training, and we have a testing. Now we can consider this training data set is 80 and testing data set is 20. Now you see that the training data set is 80 and testing is small. Okay? Training is also not that 80. So if you have some machine learning models where you have many parameters like maybe you have 40 parameters or 50 parameters. Okay, so many parameters are there, many weights. So when you have more weights, more parameters, many W's, okay, lots of W's, W1 to W50 or something. When you have so many W's, then you need lots of data, training data for tuning, because all those W's will be tuned. All these W's will be tuned based on this training data set, right? From this training data set only, this will be tuned. Now, if you have the training data is having only a limited number of images, okay, 50 images or 60 images or 60 data, then so all those parameters may not be learned properly. So we need more data. Okay, so we need, instead of 80, we need 800 data. How can we increase the data? So there are some possibilities of data augmentations. Okay, so based on which you can increase the data set size. So whatever data set size you have, 80 data, we want to increase it to 800 or 8,000. How can we do that? So we will be creating some fake data. Okay, fake data means some not real data, whatever data you have, but we will be adding some noise and increasing the number of data so that the data size will be large. How come we can do that? So there are different possibilities of data augmentations. Some of them are geometric transformations, kernel filters, color space, adding noise, random erasing, all those. Geometric transformation means, for example, if I am having a data like this, one image, I am doing something like geometric transformation, okay, flipping. So this dog is flipped, okay, upside down. I can make it left side right. Okay, so these are also some geometric transformation. Rotation, I can do some rotations, 5 degree, 10 degree. So these are the image, but I am creating more data using these rotations. I can go for scaling. I can lower the scale, I can increase the scale, I can do the translations. Okay, so this dog image can be in this side, that side, okay, in different side. Then sharpening. Okay, so these are different possibilities. Okay, so I can increase the data size. Okay, so there are different possibilities. We can increase the data size. So using this data size, so your your data set will become from 80 to 8,000 or 80,000. And then your weights will be better trained, okay, better learned. And then you can get the accuracy better, okay. Though you have high number of parameters, okay, but you, because of the low amount of training data, you could not train, or you could not tune the model properly. But you can increase the data, okay, so using some transformations, and then you can get the models better. Okay, so these are some transformations which we can help for augmentation or increasing the dataset size. Now we have some other criteria like norm. Okay, so norm and dropout. Norm means we are going to discuss. Okay, just a minute. We are going to discuss. Okay, so let us complete the regularization first, then we will discuss. Norm penalties. Okay, so norm is when we have a large number of weights. Okay, so so when we have, for example, you are considering lots of weights, W1 to W100. So several weights are there, many weights are there. And then I have some features, X1, X2, all these extents, some features are there. Okay, so many features, and these are the different weights. And then we are tuning these weights based on those features. We have different objects, data, and from those data we are tuning. Now, if you just consider one feature, okay, so let's consider X5. Let's take this X5. Now, this X5, okay, so it will affect the weights somehow. Okay, so for example, if you in some data, if the X5 is smaller, then it will affect the weights. Okay, in some of these weights, if it is large, some of these weights will be some other weights will be changed. Now, if some of these weights, okay, it's a large value. Okay, so W's, okay, one of these W's, let's consider this one of the W8 or W9. Okay, so it is very much influenced with this X5. Okay, so if with a small change in this feature, okay, this W8 is modified by large number. So for example, W8, whatever you have this change, okay, so this W8 value. So based on this a little change in these features, this W8 will be modified, or W8 will give you the results, okay, drastically. So W8 will be giving you 0.8 final output, and sometimes with small changes it will give you 0.1. So there is a drastic change based on a small change of this features. So with some features, some of these weights may be influenced a lot. So how we can tune or normalize those weights? Okay, so these are called penalties, norm penalties. So we'll increase some of the weights, okay, and we'll try to normalize the results. How we can do that? So there are actually two approaches. One is called your L1, another is L2. Okay, so L1 is you have it is called L2 is the ridge regressions, and L1 is lasso regressions. So first let me discuss about this lasso. Okay, so lasso is the or L1 regressions. So we have discussed about this loss functions. So just you avoid this part. Okay, so first you do not consider this. We have talked about this loss functions. Yesterday also we talked about this loss functions, right? This is the predictions, this is the actual value, this is the square term, and then we have this half, and then we get the error. This is the error. Okay, this is the loss functions we have talked yesterday. And today we were talking about either it could be a squared loss, it could be absolute loss, or it could be cross entropy, right? Now, instead of these loss functions, we add another term. We are adding, for example, whatever W's you have, if you have W1 to W50, okay? So we are adding a lambda of all these values, summations, okay? W1 plus W2 plus W3 plus all those. So we are considering all these weights, okay, additions, and this summation, it is also considered as loss functions to this total loss. Okay, so we got some error, and we include the total weights, okay, to this loss functions. So what is the advantage? So advantage is that if you have some weights which is actually very large, okay, or very small, then those weights will be penalized. Yeah. So because if some of the weights are very large, okay, so then you will have very large error. Okay, so this will indirectly add the total loss. If you have some weights very large, for example, W1 is 0.8, okay, or all these weights are very large. W5 are very 0.4. All these weights are very large. So we do not want this much of a high value of weights. We want small number of weights. So if you increase the number of weights, then this total loss will also be increased. So this is called lasso regressions or L1 regulation. Okay, so you have this another one. This is called L2 regularization or ridge regressions, where we consider the loss functions, okay, where these weights will also be included, but with the square term. So we are adding W1 square plus W2 square, all those terms. So if you have some weights which are very large, then their square term will also be very large, and those errors, okay, those large numbers will also be influencing to this total error. So that will try to reduce try to adjust these weights in such a way that your weights will be less. Okay, so your weight should be less. It will not be influenced much on some small features. Okay, so this either for some of these features, okay, if some of these weights are very much dependent, so it will not fluctuate much. Okay, so these weights will not fluctuate for some of these features. As the complexity is increasing, regularization will add the penalty for higher terms. This will decrease the importance given to higher terms and will bring the model towards less complex equations. Okay, so these are the two penalties which helps for regularizations. So regularization is an additional constant, okay, to the cost functions that we have discussed. So this is an additional constant. So you have this loss term, and we are adding some penalty, okay, additional loss function to the cost function by keeping the parameter more regular or normal to avoid overfitting. Okay, so it keeps the parameters more regular or normal. Now let us see some visualizations how this norm actually affect. So if you have this data set with two categories, and then if I'm not using any regularizations, okay, so maybe the model is very much overfitted. Okay, you see that the model is very much overfitted with this data set. Some of this data, you see that this is very much overfitted. Now, if I'm using regularizations with L2 regularization, this model gives you line something like this. Okay, though you have some data which are error, here in this L2 regularization, it is more or less a better model because it will give you correct results in the testing data set. Okay, so you see this in the testing data set without regularization, the accuracy was 91.5, whereas in the testing data set, if after regularization, it will be 93%. Okay. Now we have the next term as dropout. This also can help you for avoiding the overfitting. How? So what we do when we go for training, sometimes you see this model, so you have these features, you have the neurons, and you get the accuracy. Dropout means some of these neurons will not function, okay, when we do the training. So for example, these neurons, for 4 or 5 neurons, will not work, okay, when you get a model. Similarly, it will train again, and by removing some other neurons. So one time it will get the model, okay, using only those remaining data neurons, and another time it will get the model by using those neurons, and then it will take the average of all these models. So what will happen? Sometimes one of this, it will not depend on few neurons, or few neurons means few weights. So it will take the accuracy of all those models. It is not giving importance to some of those neurons or weights. So some of these weights are giving you the results and for one time, and other weights will be giving you the results. So, and then you take the average and you get the results. So removing units from the base model effectively creates a subnetwork. Okay, subnetwork means here you are not using this full network, you are creating a subnetwork. Dropout has P as a hyperparameter, means 50%, you can say that 50% of the neurons will be working in one model. All these subnetworks are trained implicitly together. So one time it will be trained, second time another subnetwork will be trained. Okay, and then later we will be combining all these results together to get the results. So okay, so for example, you are creating subnetworks like S1, S2, S3, S4, different subnetwork, and using S1 you get a results like 40%. Okay, S2 you can create a result 50%. Okay, 50%. So you will create different subnetworks, and then what would happen? When you have a new data, so you will use S1 and you see that what is the result it's saying. If it is saying, for example, it is Rahu. S2 it is saying Rahu. S3 it is saying Salmon. S4 it is saying Rahu. So most of the subnetworks are saying Rahu. So the results will be Rahu. Okay, so this is called a bagging method. So when the majority, whatever majority is saying, that is the result. So dropout helps you to not okay, so you see that some of these neurons will not be used in all the times. And then if I'm using the dropout, okay, so with the dropout, the accuracy may go larger. Okay, so when you have this accurate, when I'm using this dropout, the accuracy will be larger, and it may go for, it may increase the accuracy 95%. Now let us discuss about whatever you have these questions from this regularizations. So function of error versus parameters, find the second differential set to minimum to get to the minimum variation for training data and test data will help in minimizing error. Find the second differential set. Okay, second differential set, because you will not be getting the testing data set always. Okay, so testing data set is not available. So for example, if you are working on a competition data set, a competition data set is launched, a data set is launched for competition, and everyone is working. So they will not provide you the testing data set. They will only provide you the training data set and validation data set. And from this training and validations, you need to create the model, and that model is the final. And then you have to provide that model. Provide model means this all this weights and this architecture. And then they will test on their testing data set and see what is the accuracy. So always you will not have this testing data set in your hand. So you cannot get the model tuned based on the testing data set. So this is not possible. Okay, so you can use it when the data sets are available, otherwise not, right? So whatever you are saying, that's if I'm just going for second differential, okay, so this is possible when you have the data set, otherwise it's not possible. So sir, if add regularization to dense model, then will it affect error rate? Yeah, if I'm just adding the regularizations that I have already discussed, then it will of course reduce the error rate that we have already discussed, right, Dipti? Samir Patel, is it necessary that after using augmentation technique, accuracy has to increase? Usually the accuracy increases. Okay, so when the data size is small, when the data is very large, and when you use the augmentation technique, but it is not creating more data, more variation of the data. Okay, so for example, if I'm just saying is 0, okay, so for example, digit recognition 0. If you have some data 0 like this, okay, so this is a low variation. But if you increase, but if you have only this data, you will not get much accuracy. But if you increase the variation something like this, or you can increase the variation something like this, okay, so you are increasing the size, okay, so you are augmenting the data with the different variations of 0. So that actually tell the model that, okay, so these kinds of data may be possible. So this model will learn those variations. Sometimes this model will learn this data. So you can augment, okay, these kinds of variation, and this data set will be effective. This augmentation data set will be effective for increasing. But if the data set, you have the similar kind of data, if whatever you do this this augmentation, this does not change the variation of the shape, then there will not be any effect. If you do this, for example, if you have some data and then you are increasing the same data again and again, okay, so then it will not affect anything. Okay, same data it will not affect. But if you change the variation, of course it will. So change the variation means if you have the data 0, so it's basically some samples like this, okay. If you change the variations, okay, so it will change the variation means you are actually increasing the size and you are getting more data here and there. If you are doing the same data, so it's basically doing again here and here. So there is no change, okay, on the data space. You are not increasing the data space. When you are deforming the data, that means you are changing the data space. So your model will learn better. Okay, so your model will learn better. So data augmentation is important for this kinds of data set. Now, so digital transformations and data augmentation, the same thing or different? The digital image transformations means transformation means I'm saying this, for example, rotation, scaling, and then translation. These are the transformations. Okay, so this kind of transformation can help you for augmentations and increasing the data set. Okay, so these are only for image. You can have also some data. For example, if I'm using the ECG data or rainfall predictions, okay, some weather forecast data. So there also you can have the data set. Okay, so how can you increase the data sets? Those are also important. So in digital image, you can consider there are different techniques, okay, for the image transformation. Some of these techniques are discussed today. Okay, so there are many other transformations, many different transformations are there. Some of these transformations we discussed. Is it necessary to keep the different features in each subnetwork, or can you exchange the features among the subnetwork? See, when we are discussing about the subnetwork, so the features will be same. Features are remaining same. Okay, features will not be changed. Features are all fixed. We are only changing in this model. Okay, features will not be changed. my approach is what? Dividing exchange, conquer, divide exchange, conquer of dropout. Sorry, I did not understand what you said. Can you please write properly? Okay, so you mean that some of these features will be used one time and other features will be used another time. So it's not like that. When you will be using the model, okay, so in the dropout, so internally this will be changed. Okay, so this will create different networks. Okay, so in that architecture internally, so sometimes you will be creating S1, S2, S3 different networks. Okay, S10 different networks will be created, sub networks. So S1 will be created using some of these neurons, S2 will be created using some of these neurons. Data will remain same. Okay, so with some data, with a set of data, if you use S1, then what is the accuracy? If you have the same data, if you use S2, what is the accuracy? If you use S3, what is the accuracy? Okay, so like this. And then finally, you combine this some networks results and you get the result, final results. Okay, now let's discuss about the optimizations. Optimizations. Okay, so this is the last concept that is left for today. So optimization is, so as we were talking about this gradient descent algorithms, gradient descent means backward back propagations. You have seen that we start from this error functions. Okay, this is the error and these are the weights, and then weights are adjusted. Okay, and we want the error should be minimum. Okay, we want some error should be minimum. If you increase the weights, okay, then at some points it will be here. Okay, and it will be you will change and then you will get the errors, and if you increase then error will be large. So this is called global minimum, means global minimum, and these are called local minimum. Sometimes if you have these weights, you start with some random weights. Okay, adjust before adjusting weights, you start with some, for example, 0.5, oh sorry, 0.2. Then you see that you need to increase the weight because error is going down. Okay, 0.3, 0.4, okay, something like this. And then after sometimes you see that this error, if you increase, this error is going to jump. So that means you are stuck here. So you cannot go to the global minimum. Okay, this is one problem. Another problem is how fast you can reach to this global. So how you will change the gradients. So what is the adjustment? Okay, so how will you adjust to this? We have discussed about theta or weight t plus 1 is equal to wt plus change. Okay, so this change, how much you adjust. For example, you start with 0.2, how much jump you will give so that you can get the global minimum faster. So that means you will reach the best accuracy fastest way. So this is called optimizations. Okay, so how you will optimize this adjustment. Okay, weight adjustments. Now there are different techniques. Some of these techniques are gradient descent, stochastic gradient descents, momentum, RMS Prof, Adam. There are different techniques are there. So I'll discuss some of them. Okay, so if time permits. Hello. Hello. Regularization is you can say the sham this move regularization you can have all this, okay, augmentation, all those you can think of regularization. Penalty is for norm, okay. So norm means when I am increasing the weights, then I am giving the penalty. So that's actually for one of this regularization approach, okay. So there it's basically your penalty comes. Now in optimization, there are different optimization techniques. First one, we were talking about gradient descent. So if you remember, weight adjustment we have discussed. Weight adjustments, it was what was the weight adjustments formula? Error is equal to 1/2 summation y minus predictions. Okay, so for example, prediction is let's consider pi whole square. Okay, so this is the error. Okay, so from this error we were calculating delta W. Okay, so W1 is equal to how much W will be adjusted. You remember all those W's we adjusted last day in the last few slides. How this last slides WIK will be adjusted, WJI will be adjusted. Okay, so those are the theta. So those thetas or W's, how will you adjust? This is the error functions. This error function, it is either you can consider absolute error, squared error, or you can consider this penalty. Also you can consider this norms. Okay, this L1 loss, L2 loss, all this you can consider here. Okay, so delta G is all this loss together. Now if I'm considering, if you have 100 examples in your data set, I will not change the W's, okay, after every samples. So for example, if I'm getting one samples and whatever error I'll be getting predictions, and I'll get the some results, okay, predictions. And based on these predictions, I will adjust. I do not want that. Okay, so then that is called stochastic gradient descent. So for when I will adjust after every example, that is called stochastic gradient descent. When I will adjust after all samples, okay, so when I get the error, considering all the samples, so in 1, what is the error? In 2, what is the error? Okay, so what is the error E1? What is the error in E2? For E100, what is the error? And then I'm calculating the total loss. Okay, so based on this error, I find out the gradient and then I adjust the weights. That is called simple gradient descent, where we adjust the weights considering all the examples at once and calculating the error, total error together, and then adjust. Stochastic gradient descent is when I'm adjusting the weights after every iterations. Now you can consider that, now you can think that when I'm taking one sample at a time, it will take a lot of time. Because every time I'm adjusting the weights, it will take a lot of time. So there will be more fluctuations. When I'm adjusting, okay, so after all the models, okay, so then it will be. So here you have one graph, okay, so how actually it is converging. Okay, so if you have this SGD, okay, stochastic gradient descent, and I'm showing the plot. So for example, you have this first iteration, first few iterations, every iterations it is reducing the error. Okay, so the error is getting reduced. Okay, so this is the error functions. Okay, so first few steps, the loss will be very large, and then after sometimes it is going to be small. But you see the progress is very slow. Okay, because it will take a lot of time, and it is showing you the results on the MNIST digit data set. And there is, so we have discussed about gradient descent and also stochastic gradient descent. Now there is one between that is called mini batch gradient descent, when I want in between. So instead of taking all the samples, okay, so instead of taking all the samples, what I will do, I will take 100 examples or 200 examples, and then I adjust the weights. And next I will consider another 100 examples and I will adjust the weights. So this is called mini batch gradient descent. So first I'm taking 100 examples, 1 to 100 examples, and then whatever is the error, based on this error, I adjust. And then next take 101 to 200 examples, and then whatever is the error, then based on this, I adjust the weights. So this error adjustments will be done after some samples together. Okay, so this is called mini batch gradient descent. So if you see this mini batch gradient descent compared to this gradient, this stochastic gradient descent, so it is faster than this stochastic gradient descent. So mini batch size here it is 64. So I'm taking 64 samples at a time. Okay, so 64 samples once, and then next another 64 samples I have considered for weight adjustments. So what will happen if you are going for weight adjustment, simple weight adjustments, every weight adjustment for every data. Okay, so then it will take a lot of time, but it will be very smooth. But when you will take all the data together, yes, when you take all the data together, then what will happen? Sometimes you will see that total loss is very high, sometimes the total loss is low, sometimes high, low. So there will be a lot of large fluctuations because some of this, because of the weight adjustment, some weight is, if you are going to have, for example, 0.4, and after all this data adjustment, you will see that weight adjustments is different, 0.6, and then it will not be very smooth. In the simple gradient descent, there will be lots of fluctuations. Means sometimes the error is very large, sometimes error is small, error large, error small. So these kinds of fluctuations will be there. But when I'm doing the loss functions with every samples, then it will be more smooth. So to compromise, but this stochastic gradient descent is very slow. So to compromise this both of the things, so we use the mini batch gradient descent. Yes, there are many mathematical ways. You can consider the probabilities, probabilistic-based approach. Okay, Ganuraj. So these are all done with the probabilistic. So some of these neurons will be either on or off based on the probability. Now there is other optimization techniques. One of them is momentum. Momentum was that. So for example, if I'm getting the error, so this is the error, and then you have this adjustments. Okay, so this weight adjustments. Now you see sometimes the error is minimum, local minimum that I was telling, and then it may stuck, and then the global minimum may be here. So what we can do, if you are using, for example, stochastic gradient descent or gradient descent, so this kinds of problem may have. So but if we are using something like momentum means when you can consider these kinds of theme like idea like analogous to rolling a ball with mass and gravity on the topology of the objective function. So this, if you can consider this is a surface, and if you have a ball rolling on this surface, so even if the ball is stuck here, because of the momentum, it will move. Okay, because of the momentum as it is going down, so it will move and it will cross this local momentum, local minimum, and it will go to the next. Okay, so this is the advantage of momentum. So if there are some local minima, so there it will not be stuck if we are using this momentum. So how we can implement this momentum? So momentum will be implemented using the historical data of the gradient. So for example, initially whatever was the gradient means it was the gradient information. Okay, in the surface, what was the gradient in what is the adjustment delta? Okay, delta W, that was the gradient. Okay, so that actually we store, and then every time that gradient informations will be added. Okay, so that's actually we have this momentum. Okay, so what initially this is the gradient informations, and Vt is the momentum, total momentum. Okay, so momentum is whatever you have. For example, initially Vt minus 1 will be, for example, it is 0.1. Okay, something, and then you add this gradient, the current gradient you add, and then you get the Vt. Okay, so this Vt will be added with the weight. This value will be added with this weight. Okay, so that actually it was delta theta. So instead of the delta theta, we are saying that's Bt. Okay, so Bt is added. So Bt is the alpha of Bt minus 1 plus eta into Gt. And Gt is the gradient. So you see that every time this first gradient is stored, second time also this gradient information is there, third time. So all these gradient informations are kept, okay, in the history, and these are being added every time. Okay, so that was the idea in this diagram. So every time these gradients are added, and this information will be pushing the ball, okay, when it is stuck in the local minimum. So that when we connect, okay, this instead of the simple gradient, when in the simple gradient descent, we are using this part only. Okay, now we are using the history of the gradient. So there actually it will be better. So if we add the momentum, you will have a better results. Okay, better, faster results. I'm not going into details. Now there are some RMS props. Okay, so that's RMS props. These are using the squared gradients. So this is the formula. So this is very simple. Okay, so whatever we have discussed, you have this momentum. Instead of this momentum, we are adding this gradients. Okay, so squared gradients. This is the only techniques in the RMS prop. And then you have this Adam. So Adam also we are using this momentum and gradient both. Hello, please mute your mic. Okay. So in the Adam we are using both gradient and square gradient, both terms. Okay, gradient and square gradient, both terms. So their actually approach is better. So if you see, we are going to show some visualizations. So here, for example, you see that initially this all of this starts from here. This is the contour surface. So all this technique starts from here, and this is the solution. So which one comes faster? So HGD is this one. Okay, so this red one. Okay, so this one is going very slow. You'll see that this one will be going very slow. HGD is very slow. Whereas the other techniques, you'll see that momentum will be faster. Okay, than this HGD. And then Adam, RMS props, ADA delta, these are better, faster. So all this main idea is reach to the global minimum faster. So if I just compare all these optimizers like HGD, mini batch HGD, mini batch gradient descent, momentum, Adam, and RMS prop, so you will see that these are the real time. Okay, these examples. So Adam is this one, green one. Okay, RMS prop is this one. HGD is this one. Momentum is this. So when you reach to the solution, less error. Okay, so you see this minimum error when you reach the minimum error. Okay, so first you reach here. Okay, so this technique, it's very slow. It will take a lot of time. Whereas this one, momentum, it's very fast. Okay, so this technique, this Adam, RMS prop, this also reach to the minimum loss very fast way. Okay, so thank you. Thank you very much. So thanks for your patience, and we discussed several concepts today. Just to summarize whatever we have discussed today, we have talked about loss functions, overfitting, underfitting, regularizations, data augmentations, dropout, and optimization. In optimizations, we talked about different techniques like gradient descent, this stochastic gradient descent, mini batch gradient descents, and then momentum, RMS prop, all those techniques. Okay, so yeah, if you have any questions, you can talk. Otherwise, yeah, we can close it. Yeah, thank you very much. Yeah, so yeah, I know that we are running out of time. Thank you. So usually people use this Adam Okay, Adam RMS profs. Okay, so these techniques are better now. Adam RMS profs you can consider. Yeah, any questions, guys? Do you have any questions? Okay, thank you very much. Thank you all of you for your patience and understanding.
Thank you so much, Professor Partha, for this excellent session. So I hope, their comments are saying that they were enjoying this very much important talk. And I would again suggest that please go through this once again, so that the concept may be further clear. And in case you have any doubts, not only today, maybe you can write us your queries. We will be happy to answer you. And here I would like to make one request, that we have allowed you